All right, thank you all. So, uh, thank you for being here. The last speech of the day. So we hope you are still charged and ready for advanced solidity. So it's going to be interesting. Let's start by introducing, in the meantime, what Trader Joe is. So, well, let's start. I am DavideFi, the general manager of Trader Joe, and
I'm Louis, the least smart contract engineer of Trader Joe.
yeah, and we are very excited of being here today. So Trader Joe is the one-stop shop solution of Avalanche. We consider our DEX to be an integral part of the Avalanche community and experience. We offer many products for our deck with the Trader Joe brand umbrella. So the most common product that everyone knows here is the trading function, so the simple swap, which is what Trader Joe has been until now for trading possibilities. We have liquidity pools and farms, single reward farms, double reward farms. We also have staking capabilities as Joe, VJoe, RJoe, so liquidity bootstrapping protocol, boosted yield, and revenue sharing on the platform from all swaps. Furthermore, we have the NFT JPEGs marketplace. So I hope you have already tried the NFT platform of Trader Joe. We really like the fact that since we have launched JPEGs, there is a fresh wave of interesting new projects deploying on the chain. It has been a net growth for the overall chain in NFT activity. So we are very happy about this. And then we have Banker Joe, the lending and borrowing protocol. Let's talk about now why we are here. So we are here to talk advanced solidity, and we have our lead smart contract engineer, Louis. So Louis has an interesting story. So before we go into advanced solidity, we would like to explore a bit more his story. As you can see, he's a pretty young guy over here, but has a leading position. So how did that happen, and how it feels to be in this position is also something that we want to be of inspiration. We are here at Berkeley, where there is a very leading university. Many young folks would like to enter this space, and we think that also history could be interesting to see how we went from intern to lead. So why don't you tell us a bit how you started and how you moved to where you are currently?
Thanks, Davide. So as he said, I was a student a month ago, and I started doing Solidity in June of last year. And before that, I was introduced to all the Web3 stuff by doing bots. I was doing like little scripts to read the blockchain and give information to on Discord mostly and Telegram, so that people, if they were interested to get, I don't know, a price, a total supply, whatever, it can be hard for people to get on the actual blockchain and ask for those specific information. So that's why I've done them, and that's how I was introduced to that space. And I've done those bots for like a lot of projects in Avalanche, and that's what something I really liked about Avalanche, is that the proximity of the community, including all the protocols and things like that, they just came to me because other people were saying, yeah, this is this guy that done this bot, and if you want the same, just ask him. It's not like a closed community. It's like very open, and people share things, and if you have problem or issues or whatever, you can just ask people around, and most of the time they will answer, and they are very nice. So it was a very good thing. And Cryptofish sent me a message in June of last year, and he was asking me for the same bot because he've heard of me with other protocols. And after a while, I mean, not really a while. After some weeks, I started learning Solidity as well because I wanted to be more impactful in that space, and I really like the Trader Joe atmosphere and all the work atmosphere. And I started by mostly just trying things, testing, reading all like other people's code, like mostly Open Zeppelins, like Sushi, whatever, all the big names of like Solidity, and trying to understand, trying to get why they've done those things, and I started doing the first contracts that are used by Trader Joe, like the SJO, VJO, Rocket Joe, all those things. I was like a big part of the coding experience. Oh, sorry, no, it's too close maybe. Just I can't talk. Sorry. And like right now we have a new product which is called Liquidity Book. This is the probably the biggest thing we have done so far.
Has anyone heard of Liquidity Book here?
It's a good question. Do you want maybe an introduction of what is it?
Yes, we are going to do. Well, before we rush, so also Louis is a key developer of Liquidity Book, so that's also why this story is of inspiration. 1 year ago, he was less than an intern, and now is
that's me.
And now is a key component of our smart contracts and the overall roadmap of the project. So this is a statement that in crypto, and especially on Avalanche, has been very easy for a young, talented guy to get from zero to the top for us. And this is very important, that the fact that he can state and going to explain to you advanced Solidity. And yeah, let's just dive more into Liquidity Book.
So concentrated liquidity is a thing that allows to do basically more swaps with the same amount of liquidity, and it works by pulling liquidity in bins. So that this is a good example where you can see there is different amount of liquidity and for different price. For example, if the price is like 75, we have this amount of liquidity, and when the bin is entirely swapped to one asset, you will go to other price to then do the exact same thing until the bin is empty again, and that's how it works. Uniswap v2 used the XYK formula, which is very interesting but not very efficient for some assets, especially highly correlated assets such as like stables or things like that. This is not really interesting to use the XYK because you lose a lot of liquidity just by using this formula. So we use the constant sum pool, which means that inside the bin the price is constant, and yeah. As I said, each bin holds has their own reserves, and that's how the price can be, the liquidity can be concentrated. Yep. So it allows more efficient liquid management because you can choose, for example, different function that will allow different things. For example, this will maybe capture the when the price changed, you will capture more of that volatility, and the more Gaussian curve that we see on the left would be more to like back the price while it's important. Sorry? Oh, yeah, we have a receipt token as well for like the liquidity. Each bin have its own ERC20 that are like packed together in a kind of ERC1155 token. Do you know, guys, what's a 1155 tokens? No?
Tell us.
It's basically a set of ERC20. So that means that with only one address, you can have multiple ERC20 in one address. That is just the ID that is different. So like you have a lot of IDs, and each ID represents one ERC. And so if you own like liquidity in, for example, those 9 bins, it means that you will have 9 IDs where you will have a non-zero balance in that ERC1155 token.
Yeah, this is a more advanced way to manage liquidity positions, as for example, Uniswap v3 uses NFTs that are not fungible, while our decision to use a token will allow liquidity positions to be better managed and to unlock also protocols that can use it for different functions.
Yes. We also added search pricing, which is interesting because it allows to capture more fees when the volatility is high, to allow the liquidity provider to mitigate their impermanent loss, which is very interesting. And we do that by adding a variable fee on top of the base fee that is here to capture the volatility. Sorry. Let's now talk about advanced Solidity more. So like we will switch to code, which are like better at explaining that just.
Yeah, this introduction is because, of course, we are going to dive deeper into liquidity book contracts now. So maybe before we start, I don't know if there is any questions that we have already on the basic level, or we could go a bit deeper. Also, I'll be curious to know how many of you are developers here. Can we get a hand raised? All right, that's going to be advanced.
Yeah, I'm sorry for the others. I'll try to make it a bit easier. So this is the swap function of the liquidity book. What's important, because we're talking about advanced Solidity, the way is to optimize gas, for example. So this first part of the swap is loading all the things that you need, and this is loading them in memory so that you don't have to each time call the storage and get the value in the storage, because on EVMs, getting any value from storage is very expensive, whereas getting a value from memory is almost free. It's not free, but like it's very cheap compared to that. So for example, just here you load the pre-information to the memory, and all those things, basically, you just load everything to memory. You update the things that needs to be updated only once, because as we will do some iteration, we don't want to update things that shouldn't be updated, like more than once, I mean. And we check other things, but basically, just load things first, then the actual swaps happen. So the idea is that while the amount is not, the amount in is not 0, so that means the user send the amount in token, so let's say it's like 1 Ether or whatever. As long as 1 Ether was not entirely swapped, you just will do that again and again and again. And when the amount is 0, you will just break it and finish it and save all the things. The idea, you load, as I said earlier, you load things to memory first. Then you will get here the amounts. It's not really important how we get the amounts because it's a bit too complicated. But like you get the amounts, you then update the fees, update the reserves, and we update the amounts so that the amount out is the amount that the user will receive, and the amount in was the amount the user sent. So it was 1 Ether in my example. And we remove what we add to the reserve and what we add to the fees. Did I forget something?
If anyone has questions of any kind,
yes,
just
please
raise your hand. Any curiosity, like even why is it expensive to load the memory or things like this, feel free to ask any type of.
Why is it expensive to load the memory?
That's a bad question. It's the AVM basically. As you load the memory, or like the storage, I mean not the memory. If you load the storage of a contract, you're actually creating the blockchain, and it has to check in the Merkle tree, and all those things is kind of complicated. And whereas if you're just in memory, it's like in your state environment, and so you just don't have to query anything. So in a way, it allows to prevent spam, and it's a spam protection basically. The gas in a entire thing. And so when you load or write to storage, it's very expensive. And when you load or write to memory, it's basically free. Yep. So after that, when this is done, so that means, yeah, we will come back to that later because this is kind of cool. But like, it allows to get the next ID where where the reserves are non-zero. Sorry, but we'll get about that a bit later. And all the other things are not that interesting. And in the end, you just save all the things you've changed. So for example, you'd save the pair that we loaded to memory at first, because this changed, and you changed the fees as well, because those things have changed. And this is for the oracle. Not that, yeah, like you just update the oracle at the end of the swap, but we could have done all of this during the swap, like during inside the while block. It would have worked as well, but it would have been way more expensive because you would have stored things in the storage, which, as I explained, is very expensive. So you don't do that. And at the end, you transfer the tokens, basically. This is a really important thing to do, to always follow check, effect, and traction. So that means first things first, you do the checks. So this is, for example, that. You check that the amounts are non-zero. You check that you get the amounts. The effects are like what's happening. So like here we update the reserves. And the interaction is what you need other contract, like the interaction with other contract. So for example, the tokens. You always do that at the end because or else you can exploit things. And at the end of this presentation, I will have a little game where you can basically exploit the protocol, I mean the contract. And I would be very happy if you guys can find how to exploit the contract. Another way to save gas is to pack the value together when you are able to do so. For that, you need good knowledge of like the information that you will be able to use. For example, there are 12 variables, but it uses only one storage slot because a slot in Solidity is 256 bits. And every slot is always 256 bits. So for example, the bin step could have been a uint 256, but it's not useful because in our liquidity book, the bin step will always be 1 to 100, and 1 to 100 fits in uint 16, but it's 1 to 10,000, sorry, because or else it could have fit in uint 8, because uint 8 is up to 256. Sorry. So all the variables, you try to find the type, which is the smallest possible, so that you can pack everything together, so that it's cheaper to use. So basically, that's how you go from 12 variables to only one, is by packing things together. Using structs is very interesting, because you can load them very easy to memory, and that's what we do here, for example. Bin is a structure, and you just load everything to the memory, which is interesting, and save a lot of gas. Another example is when someone creates a liquidity pair. You need a way to be able to know if that pair was already created or not. Because if two pairs are created at the same time, it would be very hard for people, like two exact same pair, sorry, so that same bin steps, same tokens. It will be very hard for people to know which one is which one. And
what's a bin step?
That's a good question. It's the increase in price. It's a percent where the price increase. So for example, if the price is 1 and you go to the next bin, you will increase the price by the bin step percent. It was a good question, sorry. So like if it's 5%, then you will be 1, then 105, and then 101 something, because like it's percent, hard to compute by mine, whatever. So you need to store all the LB pair that was already created, and we know that the bin step will be limited to 100, like for now, and 100 pairs. We could have made 100 booleans to say this pair was created like at bin step 1, bin step 2, bin step 3, etc., etc. But it would have cost a lot in gas, as I said earlier. But as it's only 100 possibility of creation of pairs, you can fit all of them in only 1, 2, 5, 6 slots, because each bit it represents if the pair was created or not. So for example, if the bit 0 is at 1, that means the bin step 1 was created, and etc. So like if you just have to ask, is the 25 bits 0, then that means it wasn't created. If it's 1, then that means it was already created. What's important as well is to store the length, and as we have only 100 possibility, you can use the other bits to just store the length of the length, of the number of available LB pair, which is just like that. And basically, you just add 1 to this number, and that's how. This is very interesting, but a bit complicated. It does a lot of bit calculation. So if you guys want me to understand.
What makes it interesting?
Because it's cool. Like a lot of gas optimization. And yeah, it's interesting. Like instead of, it's like using new ways to get things in a cheaper way. And I find it cool, but maybe it's just me, I don't know. Maybe I'm just a nerd, I don't know. And at the end, as I said earlier, you always save the changes, because this is a memory thingy, because we always work with memory because it's cheaper. So if you change something, but it stays in memory, then the change will not happen. So you need to store it in storage after. So that's why it's that way. Yeah, we'll skip it. Skip that one. Sorry. Another way of like doing things way cheaper is to use assembly. I don't recommend to use assembly if you don't know what to do. Like
what is assembly?
It's very low-level stuff. Basically, you can do very cool thing and very bad thing without you knowing what you're doing. So don't do it if you're like very not aware of what, not aware of what you're doing. But it can reduce a lot. It's very optimized, basically. For example, this will load the exact reserves of the bin without really getting all the useless information. And so you load only one storage slot, which is right here, storage load, this specific slot. Whereas if I was doing it the other way, I would have to load it 2 times, 1 time for the reserve X and 1 time for the reserve Y. But you need to have like some calculation to like, because the one slot will contain 2 information, which is the 2 reserve. So you need to offset them by like the certain number of bits. Which here it's like 112, sorry. And if you want to only the reserve, you need to do a mask. It's a bit complicated, but very interesting.
Advanced.
Yeah, advanced. And in the end, we just verify that the reserves are just under 112. It can't be bigger than 112, sorry, because of the masks. But the reserve Y could be because you just shift it. But like, it's just to make sure. It's like safety check, because it's better to do safety checks.
Why is it better?
Because if you don't do safety check, you're probably getting wrecked at some point. Another thing which is very cool to me, it's how to calculate a power for a float. Like the idea is to do x. Oh, it's cut. I just realized. Damn, we can't see the whatever. It's power xy. So basically, you're calculating x power of y. And the idea is that to calculate x power of y, most of the time you do x times x times x times x times x times x, sorry, over and over until a y time exactly. But it's very inefficient because you're doing way too many multiplication. And another thing is that Solidity doesn't have float number, so you need to do 1 to 8. forgotten the exact name in English, sorry. But like you need to shift a number of bits that you say this is the decimals, and the other one, this is the integer part, kind of. So here, we need a lot of precision for LB. So the idea is to take 1 to 8 bits of precision and 1 to 8 bits for the integer part. And when you do x power of y, you can decompose y as the binary decomposition. So like 7, for example, is 1 plus 2 plus 4. And it's 2 power of 0 plus 2 power of 1 plus 2 power of 2. And you can do that with any numbers by just decomposing it. And it allows, that's why just here, it just checks if y is 1, y is 2. Is to, like, I mean, the bits, the first bit is 1, the first bit is a 2, the second bit, sorry, is a 1, the third bit is a 1, etc. Basically, you're checking that all the bits of y is a 1 or not, and if it's a y, if it's a 1, sorry, that means that the binary decomposition should have this exponent. It's maybe too complicated. Did I lose everyone? Sorry. Yeah, and you're just calculating over and over to get the power of y, basically. Do I have time? Okay. So I said we will be going back to this one. Maybe this is a bit easier to understand. Just the concept. The idea is that you have a tree which will store information about if a liquidity bin has liquidity or not. This is the last.
So, Louis, what are we looking at? What's that screenshot?
This is a tree.
About?
Like the last depth represents if there is a 1, so for example this one, that means that this one, because it's like that means the liquidity has the liquidity in it. The bin has liquidity in it. So that means the L is greater than 0, and if it's a 0, that means the L is 0. So by just looking at the last depth, you can already tell if the bin has liquidity or not. But as it says here, there is way too many values, like 256 power of 3, it's very big. And you couldn't, in Solidity, just iterate over and over and over and over because of the gas. It will just run out of gas very quickly. So the idea is that we have an above depth, I don't know, like a depth above it, that will represent if that specific number has at least is non-zero, basically. So that's why here it's a 1. And if it's only 0, then it's a 0. That way, and this is the same thing at the top level. And as the top level is only 256 value, it fits in only a uint, like the basic uint. The idea is that you will just have to go on the first depth, like the depth 0, look for a 1. So for example, this one. You will go down in the tree. That will tell that as like at least one of the bits here are non-zero. So we'll just search, for example, this, or not this, because there is. And that will tell you that at this specific index in the depth below, it's a non-zero somewhere. So you can just go and find the first one that you're interested in and go, basically. And that's what it's doing right there. But with a little bit of optimization as well, because this requires 3 loading of storage, because you go from here to here to here, so at least 3. And as we have concentrated liquidity, we are almost sure that if there is a 1 here, there is probably 1 very close to it. So the first thing is to check if there is a 1 in this depth. If not, so if not this block, you go to this block. It will check in this one if there is a 1 so in all of those, but like this specific depth. And if not, then you go from the top and you go down to like from the top to the very down. But this should, in theory, never happen, because when there is possibility of making money, because like if there is liquidity, someone is doing a swap, so you could make fees, someone will step in and add liquidity. So it's very improbable that you will have to go to the top. So that's why it was optimized to search first in this depth, then this one, and not the other way around. Yeah, I don't think getting very deep in that specifically is interesting. Unless someone wants to. Great. Let's play the game. It might be the interesting part. This is a bank contract. So basically people come and they can deposit their AVAX and they can withdraw their AVAX and people can do a flash loan. There is no fee or whatever because it would make the contract a bit more complicated and this is not the idea. So it's just people deposit, they can withdraw what they deposited and people can come do a flash loan so that they can use the people's what was deposited by people as long as they send it back at the end of the transaction. So everyone knows what a flash loan is, or let's say yes. But yeah, basically you just take the balance before, so like before the transaction, you send what the guy wanted, so like the amount of Ether or AVAX or whatever, and he's able to do whatever he wants here, so like he can arbitrate something, do a loan, whatever, as long as at the end of this call, he sends back all the balance. And this is just a helper function to send it or AVAX or whatever, like just the native token of the chain. So this function, you don't have to look at it, the issue is not there. In this contract, there is 2 ways of stealing money, and does someone have an idea on how to steal it, maybe? No? Do you want like more time or like just, oh, you have one?
Maybe you would call withdraw all during flash loan.
Sorry?
Maybe you would call withdraw all during. No, I think fail. Shouldn't I call withdraw all?
Yeah, it will fail because of this line, because the balance will be different. And the withdraw only the message sender money. So that means you can only withdraw what he deposited. So it will probably revert unless he send it back at the end of the flash loan, but it will be a bit weird. He will just lose money. Maybe someone has another idea? Like any answer or idea might be interesting.
So what would happen if I was to like deposit the flash loan as a way to increase my balance, but not actually pay the flash loan?
So like you do a flash loan, and here, what you're doing?
I deposit into the bank.
So you deposit.
Yes, so my balance is now
Mhm.
equal to my flash loan balance. So that I've repaid my flash
Oh, yeah,
loan. So I've repaid my flash loan without actually repaying the flash loan.
That's a way to exploit the contract, exactly. Because here you can... The idea is that during this flash loan, the balance was taken here. And when you do the unflash loan call, you deposit the amount that you just received by the flash loan. So the contract balance will increase and will be the same as the previous balance. But now you can withdraw what you deposited just during the flash loan. Basically, just you're stealing all the money that was in this contract. So this is a good way. And there is a second way, which is maybe a bit more complicated. Does someone have an idea? It's still about reentrancy, if I can give you a hint, but it's another way. Do you want a hint or like more time or?
Hint, maybe.
The hint, what can I say about the hint? It's not about the flash loan, you can forget it. It's about those 2 functions. You can do things with just those 2. Yes?
What if I overflow the user balance?
As it's Solidity 0.8, it will just revert. And like there is a second thing, the Ether, like or AVAX or whatever, it's a capped supply, which is I think AVAX is 42 million or something like that. So you won't be able to overflow even if you were to be able to overflow. But overflow is a good thing, like not a good thing, a good way to exploit things. So you should always take care of it. And that's why I highly recommend people to use Solidity 0.8 and above, because at least the overflows are checked and they will revert if that happens. Whereas if you use Solidity 0.7 or before, you really need to use safe math, so that basically just check the addition or whatever, because overflows is bad when it happens. Someone does maybe have another idea? I would just give the answer maybe. So the idea is that, or do I give the answer? The idea is that when you deposit, you will have the balance which is non-zero. So like, let's say you deposit 1 Ether, so the user balance is 1 Ether, and when you withdraw, during the send Ether, the contract is sending Ether to the caller, which we'll call this, but this is a call. When you send Ether, you can re-enter. That's why wrapped tokens are often more easy to use, because you can use reentrancy as them, unless it's like a bad contract or like a token with a callback. But like Ether is a token with a callback, so when you receive it, you can call again withdraw all, and the balance was not updated, so that my balance is still 1 Ether. So I can receive 1 Ether again, and again, and again, and again. And in the end, it will just, my user balance will be set to 0 again, and I will just have emptied the contract, basically. That's it. And that summarizes my presentation.
All right. Thank you very much. So we will really appreciate if devs or people curious to know more about liquidity book contract will approach us. We are also going to open in the next days liquidity book builders program to incentivize builders that want to build on top of liquidity book, in partnership also with Avalabs and with Chainlink. This program is going to support the builders that we participate, that will want to deploy a new product based on top of all the functionalities that they could foresee being built on top of the entire liquidity book ecosystem. We care a lot about composability and making sure that the all DeFi ecosystem on Avalanche can thrive, also thanks to the exposure that we will bring to the platform. We really believe that liquidity book is going to be the next big thing for us, and hopefully also for many new projects that will want to launch in partnership with us. So we thank you very much for listening to us today, and another applause for Louis.
Oh, yep.
I have a couple of questions.
Mm-hmm.
So the first one is about flash loans.
Yep.
I've never heard of this concept like loan for one.
Sorry.
Sorry, I never heard of the concept of loan for one transaction. Is it just for demonstration purposes, or is it a real thing that exists?
The flash loan, you mean? Yep, flash loan are used. The easiest example I can think of is to arbitrage something. So let's say on one DEX you have like 1 Ether for 1,000 USDC, and in another DEX you have 1 Ether for 2,000 USDC, but you don't own any Ether. What you will do is that you will go to a protocol that can give you a flash loan. You will take Ether, you will go to the first DEX and sell it for the USDC, and you will receive, let's say, the 2,000 or whatever, and you will use the 2,000 on the other DEX to swap them back to Ether. You will receive, let's say, 2 Ether with no slippage or whatever, let's just believe. And with the 2 Ether, you send 1 Ether back to that contract, and you can keep the 1 Ether in profit, basically. So that's one way. And there are a lot of use cases for the flash loans, and a lot of contracts implement it. Like, for example, Uniswap V2 pairs, which are probably the most used contracts in all the DeFi ecosystem, you have a flash loan. It's called a flash swap, because you can as well, you don't have to send the same token, you can send the other one as long as you're sending the same price, basically. And it has a fee on top. Most of the time, it will not just be previous balance, it will be previous balance plus a small fee, because or else no one will deposit to that contract, because yeah, you just want some incentivization, basically.
Thank you.
You're welcome.
Another question is about subnets. Is it anything like Trader Joe's logic touching subnets or anything like that?
For now, not really, because we don't believe that a DEX in a subnet would perform very well, because it would need like DRC, a bridge. It will need a lot of support, and we believe that C-chain is better for a DEX, at least for now. And we're really looking forward for the messaging between subnets. That could be interesting, because if you can, between subnet and C-chain, I mean, because now you could do things in a subnet that have an impact on the C-chain. Then maybe we will do something about it. But like right now, for us, it doesn't really make a lot of use case to use it.
No. All right, thank you very much.
You're welcome. Yep. The runner.
Thank you. How would you fix the second exploit here, the withdraw all exploit? Would you try setting user balance to 0 before doing the transfer? That has its own issues, and then, or would you change the way you would make the call to do the transfer?
Yep. I wanted to explain that, but I completely forgot. So thanks. That's a good question. How would you fix the two issues? First of all, you have the flash loan that you can do things with the deposit. Basically, you just have to add the non-reentrant to the deposit function, and non-reentrant will make sure that it's something made by OpenZeppelin, so it's like highly reputable guys. And I highly encourage you to use the libraries from OpenZeppelin. They are very great, very secure, and top quality. And when you add non-reentrant, that means until this function is completely over, so that means after this requirement, you will not be able to do anything with functions that have the non-reentrant with it. So if you add non-reentrant to deposit, you can't use the flash loan, the callback of the flash loan to deposit, because this one was not done entirely. How would you fix the withdraw one? You could add the non-reentrant as well. It works. And another way is just to swap those two lines, because it's here you're not following check effect interaction. You have you have an interaction and then the effect should be the opposite. There is no check because you're withdrawing the entire balance, so you don't have to check that like the amount is lower or equal to the user balance, because you're just removing everything. But the interaction should be before, so you reduce the user balance and then you send it. But if you do that, it will not work with that implementation, because you will send 0 Ether because you would have updated it. So you need to first cache the balance, then make it 0, and in the end, send the amount that was cached. And that's how you would make this contract secure.
Cool, thank you.
You're welcome. Does someone have another? Oh. Within LB?
You mentioned a price oracle in one of the examples.
Mm-hmm.
Is that like an on-chain, off-chain price oracle? You know, how does that work?
On LB, there will be a price oracle on-chain that will. I don't know if it's. No, you can see the structure, whatever. Inside the oracle, we will store the price, the the number of bin that was crossed, and the search pricing value. All those values will be accumulated values. I don't know if you know like the difference between accumulated and not values. When accumulated values allows you to get a time weight average something. So the most known one is TWAP, which is time weight average price. And to that, for that you use the accumulated price, and you just have to get the price that was at a certain date minus another one divided by the delta timestamp, the delta time, sorry, and you will have the average price on that period. Within Uniswap v2, for example, there was a price oracle, but you would need to build something on top of it to call every, I don't know, 24 hours or whatever, the price so that you could do a TWAP. And with LB, this is why there is some ID and some stuff, we keep all the values inside the contract. You don't have to build something on top that will query every 24 hours or like every 1 hour, whatever the windows of time you want. It will be built in the contract directly and on-chain. It's not out of-chain things. That answer the question? Perfect. That's on? Perfect. And if you have like question about Solidity or whatever, I'm gladly happy to answer them. So feel free to just come to me and ask anything.
Yeah, we are here till the end, so you have time until Friday to spend some time with Louis.
As well, yeah.
Thank you again. Thanks.